then it becomes flat, right? And so this is omega equals 0, and that's what we call DC. Everything else we call AC. DC is like a special case, right? And so when omega equals 0, plug that in. What's the impedance going to be? Omega is 0, so the impedance is 0. That's a short circuit. Right? So here's omega equals 0, z equals 0. But that doesn't apply at high frequencies. So as you go toward an omega of infinity, in fact, the impedance becomes infinite, and inductor begins to look like an open circuit. Right? So high frequencies, infinite impedance. 0 frequency, 0 impedance for the inductor. The capacitor, of course, behaves in the opposite way, and the circuit symbol reminds us of that. The capacitor looks like a broken wire, right? So at DC, we see the impedance, again, is 1 over j omega c. So if omega is 0, when you divide by 0, you get something that's infinitely large, right? And so it becomes an open circuit at DC. And then at very high frequencies, when omega is infinite, this becomes very, very small, approaching 0. And so a capacitor looks like a short circuit to high frequencies. This is a really good, quick test that you want to kind of intuitively remember. Because when you look at circuits, as we move toward these more complicated circuits and doing frequency analysis, you want to very quickly identify what's happening at low frequencies and what's happening at high frequencies. And so, of course, the extremes of that are 0 and infinity, right? So if I were to look at a circuit, and if I had, as we start thinking about filters, and I say, well, here's an inductor, what is that going to let go through? Well, it looks like a short circuit to DC. So low frequencies can go through an inductor. But high frequencies, this looks like an open circuit, so high frequencies can't go through. Right?
Is there like a limit where
typically we'll see this when we do the filtering part. They'll often define the 3 dB point. So they'll define the point where basically the power cuts in half. We'll talk about the decibel scale and what exactly that means in later chapters. But that is sort of where people define it, and they'll call it the corner frequency. And so it's kind of like, if I started out with this much, and then I look downstream and it's only this much, they'll say, well, I've pretty much cut that off and not let it go through. Because anything, if in the case of an inductor, any frequencies higher than that would really be reduced in power, right? They really would have a hard time getting through that inductor. And then the capacitor, again, just the opposite. Capacitors are also oftentimes called DC blocks. So like on your oscilloscope, you guys remember in the lab with the oscilloscope, you could put it into the DC or AC coupled mode. I don't know if you played with that at the end of the semester a little bit. But you can put it into AC coupled mode. And what did that do? Well, if you had your, especially when you're doing like the instrumentation amplifier, that instrumentation amplifier lab, you might have had a DC. So if I'm looking at my plot on my oscilloscope, the DC bias that you put into your instrumentation amplifier, then you had a little wiggle on it from the function generator. Right? And if you looked at that in the oscilloscope and you pushed the AC coupled button, it would have immediately looked like this. Why? It inserts basically a capacitor into your circuit. And so the DC can't get through. And you can only get the high frequencies. And something has to be changing in order for it to get through a capacitor. And you can think about what is physically happening there. Well, again, capacitors, there's only current through a capacitor when there's a derivative as a function of time. So DC, if there's no derivative, DC, there's nothing changing, so the derivative is 0, so there's no current. So no current can actually flow into your oscilloscope. And so it has nothing to measure. But then if something starts to change, a little bit of current gets through. What's happening, as it's changing, some charges are piling up on this side. Some positive charges pile up over here. That sucks negative charges to this side. And then as the voltage swings the other direction, the positive charges come off, leaving negative charges behind, and that pulls positive charges to this side. And so the positives and negatives are flipping back and forth, right? So they're not so much going through as they are, when positive comes here, it sucks negatives here to this side from the ground of the other machine. So your electrons, right, are actually getting pulled out of the earth onto the other plate right here. If I put a positive charge on this side of the plate, this side of the plate sucks electrons up from ground and puts them on the plate. And then when I push negative charges on this side, it pushes all of those negative charges away. All those electrons shove down and go back into ground because they want to get away from those other negative charges as fast as they can, right? So that's physically what's happening. So you're not actually getting electrons coming to this side, hopping over that gap, and moving through. That does happen in some devices, but not in a basic capacitor, right? In fact, for most instances of electrical engineering, that's a bad thing. If electrons start actually jumping across your capacitor, you're going to burn it out, right? Because they're not supposed to do that. That's called a lightning bolt, right? when electrons move from one spot to another spot by force, right, something has to blow up. And so that's not usually good. So most of the time, it's literally just sloshing electrons back and forth from one spot to another. Right? And again, we'll see as we get into the frequency domain analysis, in much more detail, how important that is and how that works for creating filters and circuits that start to do interesting things. That's one thing too. Last semester, I think I mentioned last semester, that unfortunately the first class in circuits is kind of boring. Like, the circuits don't really do very many interesting things, and that's because we restrict them just to DC. So you can turn a battery on, you can turn a light on, something like that, but like, how does that then become a computer doing something, right? That's a lot more complicated. Well, we're building up to that, right? It's going to start to get a lot more interesting in terms of what can we actually do with these circuits, right? We'll be able to build filters that can shape the sound of music that we hear using the concepts that we're learning in this class this semester. You're going to start to see that, you can turn power from a wall socket into DC that could run your laptop, right? So there are lots of different applications now as we start looking at varying frequencies. We can start to do more with our devices, with our circuits. And then next year, when you go into electronics, you'll start to learn in more detail how transistors and diodes behave. Then you start getting into the really interesting parts where you can say, oh, now I can actually turn things on and off. Now I can make a switch. Now I can do digital logic. Now I can actually do computations and transfer information, and so it all builds up. You guys are all in digital, right, as well this semester? Did anybody not get into digital yet? You haven't taken it yet?
I might get it later.
You will. Okay. You've had some experience with it before. Good. Good. Yeah. So so as you're seeing digital, you guys are dealing with that from a very logic level, right? You're doing like all your Boolean operations, right? What's an and, what's an or, and you're adding ones and zeros, and like how does that relate to the electronics that we're doing? Well, ultimately, it comes down to transistors, which we haven't dealt with a lot in the class, but next semester you'll see those transistors. They act like switches that actually turn on the ones and zeros for you. And so you'll be able to see where those logical functions come from. So it does get a lot more interesting than just, let me plug in a battery and light up a light bulb. Right? So anyways, so once we do this transformation into impedance form, we can use our standard KCL, KVL, all those theorems from chapter 4 that we did before, doing superposition and linearity, all of that applies, right? And we can use that to solve circuits directly. So if I have a simple circuit like this, and I want to write down the impedance form and do the solution that way, this is just an RL circuit, which we learned how to solve in chapter 7, but now, let me do this transformation into the impedance form. So how do I put the VS into impedance form? Or into phasor form, I should say. What is the phasor form? Come on, Andalib, I know you want to say. What's the phasor form of 5 cosine 10t? What are the two parts we write down for a phasor?
Amplitude?
Yep. Which is?
5.
Yeah. And then the other piece? There's an amplitude and there is an angle, a phase. And so the phase of this one is?
0.
Yeah, 0. Because there isn't any explicit phase. So we can write it down as a 0. So also, let's identify and just kind of tuck it away, right? What's the omega? 10, yeah. So I'm going to need that, right, in a minute, because I want to transform my resistor and my inductor into phasor form, into impedance form. So the resistor in impedance form is just R. So that stays the same. It's still 4 ohms. But now this 0.2 Henry inductor, I need to turn that into its impedance, and the impedance is, for an inductor, J omega L. So let me calculate that. Omega is 10, L is 0.2, so that gives me 2 times J. Right? So that's the phasor or impedance form of the inductor. And now I can figure out, they want me to find the voltage across the inductor and the current in the loop, right? So I can do that. I think probably finding the current in the loop is the easiest. So how do we find the current, the mesh current? What do we apply to find a mesh current?
KVL.
Yeah, do KVL around the loop. So I go around my loop, right? I start in my lower left-hand corner from my preference. I go clockwise around the loop. I hit the minus sign first, so that's -5 with an angle of 0. Right? And then I do I times R, right? Plus I and then times R, so that's the 4 ohms. Plus the voltage drop across the inductor, right? But I now have it in impedance form. That's like an R, so it's just I times R. So plus I times J2, and that equals 0. And I have one equation, one unknown, and I can solve for I. And how do I do that? I'm sorry, this is the one part where I said like it gets a little funky, because now I've moved to phasor form, I should use a capital I. But typically we use capital I's to represent branch currents, not mesh currents, but now we're gonna break that trend. So now I can just factor out my I. Sorry. So I4 plus J2 equals, and I move this 5 over to the right-hand side, 5 over 0, and then I solve for I by dividing. That's my answer. Now I need to do a little bit of the complex number gymnastics here to simplify this. Right? I should put if I'm doing it by hand, I should put the denominator into polar form. So I'd have to take the R, I'd have to go, square root of 4 squared plus 2 squared. So that's 16 plus square root of 20, which is not a nice number, right? Square root of 20. So it's 5 divided by the square root of 20, and then you subtract the angles, right? Since I already have the answer written down, once you've done that, you are going to go back into the time domain, right? Shift it back to the time domain so it becomes little I of t, and then the magnitude of that, which worked out to be 1.118, is times the cosine of omega t. Omega never got lost. We had it right here all the time. So that's just 10t, and then the phase worked out to be the -26.56. Which means this guy down here must have had a phase of 26.56 degrees, because then it's 0 minus 26. And so that's I. But once I know I, can I find V? Sure, right? But I want V on the inductor. So again, the voltage on the inductor is L di dt, right? But we don't want to do that. We don't want to do derivatives. Yuck, right? Why do that? I have a perfectly good phasor form of I right here. And so what's the relationship between I and V? Well, V equals j omega L times I. So once I have this, I can just multiply. So the j times the 10 for omega times the L, right, which is the J2. That's what it's become in phasor form, J2, times this I right here, the big I. And then that I can transform into the V of t form, little v of t, right? Time dependent. And again, it works out in phasor form. I have it written down. So when we multiply, here's a 20 times 1.118, you get 2.236. The j times the j gives a negative 1. And again, you're going to be 90 degrees off on the phase here. So add 90 to the 26 and you get the 63. So that ends up with what we have on the board. Right? And I have the voltage. And I never had to do a derivative. Right? So everything we learned about nodal and mesh analysis applies. We can do KVL and KCL in the phasor domain, which is usually called the frequency domain, just as easily, except that we have to deal with complex numbers. That's it. That's the only complication we're adding. It becomes more complex. Right? So everything else is the same. And we can do math in the complex domain just as easily. And more importantly, MATLAB can do math in the complex domain like nobody's business. It doesn't care. We might care. I might see an I and say, oh, what am I going to do with? Why do I have to deal with that, right? But MATLAB, it doesn't care. MATLAB can do all of those polar to rectangular conversions for you. You can type them all in together, and it won't care. It will just calculate them, right? So MATLAB is your friend, even more so than it was before, right? We can do, as I mentioned as well, we can do all of the impedance combinations that we found that we did in DC analysis. We can do voltage division now across a resistor and an inductor. Why not? If I wanted to know the voltage out here, in fact, I could do voltage division using this, right? I could say, I don't even have to go through this whole process because voltage division is even easier. What's the voltage across this resistor, if this were a resistor, right? Well, that's pretty easy. VO equals VN times R2, right, which is J2, divided by the total resistance, 4 plus J2. And that's it. VN is 5. Let me substitute that. And I'm done. I just found the voltage out on the inductor, right? That's just multiplication. Again, MATLAB will do that for you just as fast as you can type it in, right? Okay, 2 milliseconds slower than you can type it in, right? You have to hit enter. So, and that's it, you're done. And if we were to run this calculation, we would get that exact same number that we got in the previous equation, right? So voltage division works. Current division works. Same thing. Circuit reduction, I already mentioned. We could combine both of these. If I wanted to know I in this circuit, I could combine it into something like this. Where this is 5 with an angle of 0, and I have an impedance of 4 plus J2. Right? So now I want to know I. What is I? Well, that's just V over Z, right? So I equals 5, angle of 0, divided by 4 plus J2. Wait a minute, doesn't that look familiar from the previous equation we just did? I mean, like 2 equations ago when I did KVL around this loop, right? That's the exact equation that we wrote down. And I did this way by doing an impedance combination instead, right? So you can do equivalent impedances to reduce your circuits. You can do Y delta transformations. even better, right? We love Y delta transformations. They're so much fun. So we have some little tools on MATLAB, right? I have those little script files to do Y delta transformations for you. Each element of the array can be complex. So it could be a resistor and an inductor combination. It could be just a capacitor, or capacitor and an inductor. Write them down in the array, and it will do the transformation for you just fine. Right? That Y delta and the delta Y M files that are posted, if you don't have them from last semester, you can download those. Okay. So all of these combinations, again, we can reduce something like this. Now we're safe to say, wait a minute, these are in series. That's in parallel with this. And then that combination is in series with these two. Right? And I can write it down. And another thing to point out on this, in fact, don't get confused with a capacitor. When we dealt with capacitors before, when we were doing like two capacitors in parallel, we said they added in the reciprocal, right? Two capacitors in parallel added directly. They behaved opposite of resistors. Now they don't. Now they don't. So a capacitor in series, if we put all of this in phasor form, right, and we're told in this one omega is 10, so this capacitor and this resistor just add. It's not like this one's reciprocal or anything like that. Why does that work? Well, it's because we actually